Hi everyone. In our last video, I talked about ways of measuring vision in terms of our ability to see detail, which is called acuity. Another way to think about vision is our ability to pick up differing amounts of light, and that leads me to brightness. Now, we're going to have to understand a little bit of physics, as we did with acuity as well, just a little bit of physics. There are units called photometric units, and this comes from a branch of physics called photometry, which is about measuring light, specifically visible light. Now, to see anything, we have to have light. I know that's obvious. In physics terms, this is radiance, and we can measure this in units of radiant power produced by a light source, and the units are lumens. That is the technical term. A lumen is the amount of light produced by a standard beef tallow candle called a candela. Yes, it's made out of cow fat. It is a standard candle. And if this helps you at all, 1 lumen is 1.46 milliwatts. Does that help you? Probably not a lot. Although, this might sound a little bit familiar, the units of lumens, if you're really into light bulbs. So I want to compare and contrast incandescent, compact fluorescent lights, and LED light bulbs. So let's first take a look at incandescent bulbs. So I just picked a particular brand. Now you would buy them according to the wattage. Like, I need a 25 watt bulb for the lamp in my nightstand. Okay, you don't want to have a super lot of light. And in this case, this particular brand outputs 210 lumens. Really what you're saying is, I want this much light output. The power is actually the power consumption. Most of the power is actually going to be converted into heat. Have you ever touched an incandescent light bulb? You could burn yourself. Those suckers are hot because the vast majority of power is being converted into heat and it's being lost. We want things to be a bit more efficient. So this brings me to compact fluorescence, the common spiral bulbs. So for a given amount of radiance, they're a lot more energy efficient. So I've kind of tried to find some sort of kind of comparable ones. So a 7 watt bulb is something you might want to put in the lamp on your light stand so it's not too bright. So a lot less power consumption, but still the majority of power is going off into heat. Well, technology progresses and we have LED light bulbs now, and these are even more energy efficient. They're not really that hot to the touch anymore, and they don't consume as much power, but a lot of that energy is now into radiance. I think there are laws that require the packaging of light bulbs to show you the lumens. That never used to be a thing. So really what you want to look for is a certain amount of light output with the least amount of power consumption. Okay. No, this is not going to be on an exam. Think of it as a public service message. You're welcome. Okay, so to see something, we need to have a light source. Okay, that's the first thing. But then what are you looking at? You're looking at something. That light has to be falling on a surface. I suppose you could be looking directly at a light bulb, but I wouldn't recommend that. The amount of light that falls on a surface is called illuminance. Have you heard the word illumination? That is the same thing as illuminance. Now here, because we're talking about a surface, the units are called lux, which is defined as 1 lumen per square meter of area. So 1 lux is 1 lumen per square meter. Just to give you some numbers if this helps, daylight is 10,000 lux and the full moon is 0.1 lux. And again, we can see by the light of the full moon as well as in daylight, and that's quite a range to be able to see. So the surface is appearing because there's an area. So we're talking about light falling onto a surface and illuminating it. But we have to get that light bouncing off of the surface into our eyes. So we need more than illuminance. What we end up with is luminance. Now this is light that bounces off of the surface and now it can potentially go into our eyes. Once again, we have to have a different unit because we're talking about kind of a different aspect of light. The unit is called a nit, and it sounds kind of silly. So a lot of people do not use the unit nit, but they actually use the underlying units called candela per square meter. This is a bit different than lumens per square meter. A candela is, again, the amount of light being expressed into a volume of space. So if light strikes a piece of paper, it's going to bounce off, but it can bounce off in a whole bunch of different directions. Using a candela captures all of the directions in which the light might be bouncing. It's kind of a technical thing. You don't have to worry too much about that, but it is important to know the difference between illuminance and luminance. So what is the difference? How do you keep them straight? They're so easy to mix up. Okay, so take a look at the words themselves. Illuminance, luminance. It's like, oh, look, there's something being held back. You're missing the I and the L. So any surface is going to absorb some of the light, and then the rest of it is going to be reflected back off again. So if you think of a surface as holding back the I and the L, what's coming off of it is the luminance. You start with the illuminance, you end up with the luminance. Does that help? Look, I'm just trying to help people. If this doesn't help you, make up your own thing. And if you come up with a better way to sort them out, post that on the discussion forum. Here are some units for luminance, and you might think, I've never heard of this before. You know what? Yeah, you probably have. If you pay a lot of close attention to your computer monitor. So old cathode ray tubes, the old kind of boxy monitors. My old one put out 150 nits, and that thing sucked down a lot of power. If you touch the back of it, it would actually be really hot. LCD monitors or LED monitors these days put out a whole lot more light, and they're way more energy efficient. Another public service message. Okay, so there is this relationship between illuminance and luminance, and that depends on the property of the surface. Here's another physics unit for you, but this one isn't too gnarly. It's simply reflectance, and it is the proportion or percentage of light that is reflected from a surface. So clearly the units are percent, but you know what? We're not going to let that go. Oh no, we're not. We're going to introduce a new unit called albedo. Albedo is luminance divided by illuminance multiplied by 100 to get rid of the decimal points. And if you pay close attention when you're buying paper for your printer, the higher the reflectance, typically the more expensive the paper it is. So black paper is about 10%. You might be thinking 0. No, it's not 0. Even super black paper does reflect some light. It's not a black hole, okay? White paper is about 90%, and you can go above that. So again, the higher the reflectance, the higher the albedo of the paper, the more it's been bleached, and the more expensive it usually is. Okay, but so far, all we've got are physics units. Where's the psychology? Okay, psychophysics, people. I got to talk about both sides of that. Okay, let me go to the psychological dimensions. Brightness now kind of goes back to that property of radiance, the intensity of light. Brightness talks about your experience of the intensity of a light source. Now, you can't use brightness to talk about anything that is not a light source. You can't say, whoa, that's a really bright shirt. Unless that shirt has light bulbs in it and it's emitting light, technically, that is not the correct term to use. Brightness applies just to a light source, okay? Important thing to remember. And I'm really emphasizing this because, again, there are terms that are really easy to mix up. There is brightness, and then there is lightness. Again, this is a psychological dimension. This is a dimension that applies to a surface. We're not going to be talking about color. We're going to leave that out for now. We're going to bring that back eventually after the first midterm. Lightness refers to the property of a surface ranging from white to gray to black. Again, we're not going to worry about exactly what color it is. We are talking about a matte surface. We're not talking about mirrors, okay? Lightness is an inherent property of a surface. Now, brightness, lightness, very similar words. Make sure you don't confuse them. Just to confuse things a little bit more, if you're interested in this, lightness is the term that is used in North America. I actually prefer the term that they use in Europe, in the UK. They actually use the word whiteness. And I think that's a whole lot clearer, but it doesn't appear in the textbook, and people in North America will go, what are you talking about? So again, we're going to be sticking with brightness and lightness. So I want to go to brightness perception. There are various factors that affect our perception of brightness. And this includes, what is your current state of adaptation? So dark adaptation and its opposite, light adaptation. Are you in a bright movie theater lobby? Or are you in the movie theater itself when they've turned out the lights and the movie is starting? So this is one thing, your state of adaptation. There are some other factors called retinal locus. And this is a callback to something I talked about previously, the location on the retina. In your periphery, your threshold is lower. That is, it takes less light to activate the photoreceptors in your periphery because of rod convergence. Now again, this is exactly the same concept I talked about. I used slightly different terms. I did use the word summation. This is just another way of describing the same thing. Now what I've got over here on the left is a chunk of your fovea with a bunch of cones, and I've got two beams of light. But these, I've tried to draw them kind of gray, meaning that they're less intense. So it's a very dim light, two very dim beams of light. Now our cones, you'll remember, are less sensitive to light. And it turns out these two beams of light are not strong enough to activate the cones. That's why they're black. They're not being activated, and neither are the corresponding neurons. There is light landing on the fovea, but it's not enough to cause any neural signals. This light is invisible to you. This might happen if you're way out in the country and there's no light pollution from the city, and you look up at the sky and you might be amazed by all the stars that you can see. But if you try to look directly at a dimmer star, it'll disappear. You can't see it. But if you look just off to the side, you can see it in your peripheral vision. Let's see what's happening in your peripheral vision. So this is your periphery, where you have a lot of rods. Rods are just inherently more sensitive. So these rods are being activated by these two dim beams of light. They send their signal down to this neuron. Let's say the threshold for this neuron is 2. If there's just one beam of light, there's just not enough light to cause any neural signal. But in this case, there are two rods that are activating this neuron. It's going to fire, and you will be able to see that dim star in your peripheral vision. But if you look directly at it, no, you can't see it. It's disappeared. Drives you crazy. Okay, adding a bit more complexity back, we will fully consider color and wavelength a bit later on, but we do need to introduce it here. Wavelength is an important factor in brightness perception. Now there's a few ways of doing this. You can be presented with a standard color and then a bunch of comparisons and adjust them until the brightness is equal. This is tricky to do because, again, they are different colors, and you have to try to ignore the color and just focus on their brightness. You can do it physiologically, getting the absorption spectrum, something I talked about in a previous lecture. We can do this under different illuminations. We can try it under photopic conditions, and then again under scotopic conditions. And it's going to turn out to make a lot of difference. When we're undergoing dark adaptation, again, we've gone from the bright lobby into the dark movie theater, we've shifted from relying on our cones to relying on our rods. There is also a change, a shift in the wavelengths that we are most sensitive to. This shift is called the Purkinje shift, dating all the way back to 1825. And in general, when you go from a bright condition to a darker condition, your peak of sensitivity is going to shift to shorter or bluer wavelengths. summarize this in a graph. Here's a graph that illustrates the Purkinje shift. Let me describe what we've got. Okay, the top curve represents our photopic sensitivity. So under fairly light conditions, this is the sensitivity of our cones, basically by themselves, because our rods are going to be overwhelmed because there's so much light. Our y-axis is relative sensitivity from 0 to 1.0, and then the x-axis is wavelength. So 400 about here, 500, 600, 700. So blue into the greens, and then the red over here. Our peak of sensitivity under bright kind of daylight conditions is right about here. It's about 550-ish or so nanometers. That is kind of a lemony, kind of a limey green, so a yellowy green. That is the one wavelength that we are most sensitive to. However, you turn out the lights, and this entire curve shifts over to the left. Now remember, the rods are really not sensitive to the longer wavelengths. Sorry, let me bring that back. Okay, so our rods can't pick up the longer wavelengths at all. We're no longer relying on our cones. There's not enough light to activate them. So what we've actually got is the response profile from the rods by themselves. And just inherently, the rods have a sensitivity that's shifted toward the bluer end of the spectrum. If you ever get up in the middle of the night and you go to the bathroom, you don't want to turn the lights on, everything around you might kind of sort of look bluish. There's some light leaking in from outside, maybe street lights or moonlight, and if everything looks kind of bluish, it's not necessarily that the light itself is blue, but the red light you're really not sensitive to, and you're more sensitive to the bluer part of the spectrum. So the difference between our photopic and scotopic sensitivity is called the Purkinje shift. And there's mercifully, one last factor, well actually it's a 2-for-1, that affects brightness perception. It is time and area. Time means the longer a light is on, the brighter it's going to seem to be. Now this doesn't mean for an hour. That's not going to work. In fact, the opposite is going to happen. It's going to seem less bright because your sensitivity is going to decrease. We're just talking sort of fractions of a second. So the longer that light is on, the brighter it will seem to be. Area as well is an important factor. Kind of the larger the light is, the brighter it's going to seem to be. And again, this is under not like I'm talking like 1,000 meters. It's just fractions of visual angle. At this point, we've now considered the limits of vision, both in terms of visual acuity and our ability to pick up brightness. We're going to want to put those two together, but before we do that, we're going to have to take a little bit of a detour and understand a little bit more about neural processing. So I want to continue to follow the path that the information has taken as it's entered into our eye. So if you remember all the way back, we've had an object, light strikes it, light bounces off of it, it goes through the pupil in the center of the iris, it goes through the crystalline lens, it lands on our retina. It then lands on rods and cones. When they become active, to oversimplify a little bit, they'll be sending connections to bipolar cells and then to retinal ganglion cells. And those retinal ganglion cells are going to send their axons outside of the eye to send information back to the brain, which we will be coming to eventually. But before we get too deep into the brain, I just want to stay in the retina for a second. I want to describe the optic nerve. Now, this is the collection of axons of the retinal ganglion cells collectively together called a nerve. Again, we have to have some way of carrying the information from the inside of the eye out of the eye. So yes, there was that point that I pointed out to you where there are no receptors. It's called the optic disc, and that results functionally in a blind spot. If only there was some way I could get you to measure your blind spot in each eye. If only there was some... Oh, that's right. There's a lab that's going to get you to measure your blind spot. Now, in the retina, there is the processing of information, and we know that just by looking at some different numbers. We have on the order of 126, 130 million receptors, the rods and cones, but there are only about 900,000 to 1,000,000 nerve fibers, that is, comprising the optic nerve per eyeball. Now that's a pretty big discrepancy. How did the 126 go down to 1? How exactly does that happen? Is it just random connections, or are there patterns? Okay, this is where I want to introduce a way of describing the patterns, and the concept is called a receptive field. It's a little bit of a tricky concept because you have to juggle a few different things to understand this one concept of a receptive field. The first part, and it's in here in the definition, there's a stimulus. Okay, so there's something out there in the world. There is a visual stimulus. We are assuming there is light falling on it, bouncing off of it, and then bouncing into our eye. And this particular stimulus is landing on a certain area of the retina. It's not just that there's light flooding and hitting the retina, but it's a particular pattern. And if we get this particular stimulus falling on this specific part of the retina, it can influence the firing of a neuron. So the receptive field does talk about kind of an area out in space, but also an area of the retina. It's also talking about the firing of a neuron. This is what I mean by juggling. We have to think about a distal stimulus, a proximal stimulus, or at least a certain area of the retina, and then at the same time, a neuron firing? Now that's a careful choice of words, neuron, not a rod or a cone, okay? So not a photoreceptor. That is implied, as we'll see coming up. I've got some diagrams that will show you some simple receptive fields. The simplest receptive field is found in ganglion cells, and it's called a center surround. So I have to describe what you're looking at here. You have to imagine that you're looking at the retina, and we're looking at a kind of a roughly circular shaped area. And everywhere in here, I haven't drawn it, there are receptors. Tens of them, or hundreds, or maybe thousands of them. Now, there's nothing you can really tell by looking at the receptors themselves, but some of the receptors cause an excitatory signal to be sent. And that's all the receptors in this area, in the center of the ring, in the center of the donut, in this timbit here. Okay, so if light falls on this area, it's causing receptors to release excitatory neurotransmitter. But if light falls on this donut, it activates the photoreceptors, which release inhibitory neurotransmitter, either directly or maybe indirectly. So I'll get to that in just a second, exactly how that happens. This shows the two possibilities of center surround receptive fields. We have an excitatory center, inhibitory surround, and then the exact opposite. Again, I'll get into those details in a second. How do we get these receptive fields? Well, again, there are tens, hundreds, thousands, maybe even millions of receptors that all send their signal to a single ganglion cell. And we might have a microelectrode plugged into this ganglion cell, and we're taking a look at its firing rate, and we're presenting different stimuli to this area of the retina. We're presenting different kinds of stimuli, points of light, or bars of light, or maybe circles of light, or donuts of light, trying to determine what is the receptive field of this ganglion cell that we're plugged into. Okay, now I need to zoom in and give you a bit more detail because that was a bit too simplistic. Okay, so let me describe again what we're looking at. This is a schematic diagram. It doesn't literally look anything like this. Okay, so this kind of grayish chunk up here represents the retina, and all of these little R's are receptors. So it says rods or cones, could be either one. We're not going to worry about that. Now, these receptors don't look different from each other, so we don't really need to worry about that. They actually will all be excitatory. So, adding a little bit of complexity back, and we know that they're all excitatory by looking at these. So these are representations of their axons, basically. And they all have arrowhead endings. that is the schematic representation in a neural wiring diagram for an excitatory synapse. Okay, so they are all excitatory. And what that means is when each receptor is struck by light, it will release some excitatory neurotransmitter. Okay, but then we have to take a look at the next set of cells. So let's see what happens if we shine some light on the timbit, okay, the circular area in the center of this center surround receptive field. Okay, light is going to strike these receptors, and they are all going to release some excitatory neurotransmitter, and that will activate this bipolar cell. It will reach its threshold, and it will in turn excite this ganglion cell. Okay, that's why this is called the on area, or the plus. If light strikes this central region, it's going to increase the firing rate of this ganglion cell. Okay, but now let's see what happens if light strikes the donut-shaped area, and only the donut-shaped area. Light will strike these receptors, it will activate them, and they will in turn activate this horizontal cell, and this one too, and they are both going to inhibit this bipolar cell. So this T-shaped ending represents an inhibitory synapse. So now, of course, the ganglion cell is not going to increase its firing rate. One last possibility, what if there's just diffuse light and it's striking all of these receptors at the same time? We're going to get some excitation, some inhibition, and they're going to cancel out. And the ganglion cell is not going to change its firing rate whatsoever. Now this is a highly simplified diagram. It does leave out some detail, but it gives you the basic idea of the center surround receptive field. So my point in showing you this is multifold. So first of all, there's a lot of processing that happens very early on in the incoming stream of visual information. It's pretty complex processing as well. But if we try to take a step back, what exactly is this center surround receptive field doing? The one stimulus that is maximally going to excite this ganglion cell is a circle of light surrounded by a donut of darkness. How often do you look at a circle of light surrounded by a donut of darkness? I really gotta think. Looking at the full moon, I guess? But beyond that, when am I looking at something that has bright and then dark? Well, we will eventually work towards these receptive fields working together. What they're really doing is looking for contrast. Contrast between an area of light and an area of dark. Both the on center off surround and the opposite are both doing that same thing. They're looking for contrast. So the fundamental building block of our visual system, we can tell already, is contrast. Put a pin in that. We're going to come back to that later on. But I do want to explore a bit more neural processing. The fact that these horizontal cells are sending an inhibitory connection off to the side. Now there is a term for that. It is called lateral inhibition. So inhibition means inhibition. I mean, that's what it means. Lateral, of course, means off to the side. So here's another view of what might be happening in a center surround receptive field, stripping away even more stuff. So we've got a few photoreceptors here. We've got 3 from the center and then a total of 4 from the surround. So I've taken a slice through it. We have some excitatory connections here. And then also, importantly, inhibitory connections coming from the sides. This is very basic processing, but it turns out to be very powerful. We can do some very powerful things if we harness this lateral inhibition. And without going too deeply into the details, why is it inhibitory? Well, there's inhibitory neurotransmitter being released. Okay, let's see how lateral inhibition might be employed to explain some lightness illusions. So here's one called the Chevreuil illusion, dates back to 1861. So let me tell you what you see, that is, what your perception is. So we've got a bunch of bands going from lighter to darker, but if you pick an individual band, on the left side of it, it looks like it's kind of really dark here, and then it fades and gets lighter. Each bar seems to be doing that. On the left side, it's darker, and as you move to the right, it seems to be fading to get lighter. Okay, that's your experience. Now, what this actually is 7 bars, and each one of these bars is painted with a consistent shade of gray. So the artist hasn't like faded it from dark to light. No, that's all happening in your perceptual system. How does this work? Maybe, yeah, I know, you saw it coming, maybe lateral inhibition. So I want to explain it. I don't need 7 bands. I'm going to highly simplify and just pick 2 bands. It'll still work. Okay, so at the top, I've got my 2 bands, a slightly lighter gray and then a slightly darker gray on the right. What is this? What is this step thing? You can think of this as a little graph. And what this graph is graphing is the differences in how much light are coming off of each of these bands. So this band on the left is a bit lighter. I'm using that term carefully. And this one over here is a little bit less lighter. Okay, so it's a step function, it's a little graph, and it shows an abrupt transition between the 2 bars. Next, we've got some photoreceptors that are looking at these 2 bars. So yes, there's only 4. Again, highly simplifying. Okay, now these receptors, when they get activated, they're going to send a certain signal down this way. But I've also drawn them with these little arms off to the side. Arms with T-shaped endings, meaning it's inhibitory. So each one of these photoreceptors is inhibiting its neighbors on either side. Again, this is not exactly what the photoreceptors are doing. There are other cells that are doing this, but I'm really oversimplifying here. Okay, let's look at the numbers now. So these 2 photoreceptors are looking at this lighter bar, and I'm saying they're getting hit by 100 units of light. These 2 over here are looking at the darker bar, so they're only getting hit with 20 units of light. Okay, so far so good. But now what each receptor does is it takes a proportion of that activity and sends some inhibitory signals to its neighbors. Again, to work with some nice round numbers, I'm going to say it's 10%. So this receptor here is sending -2 to its neighbor over here, -2 to its neighbor over here. Likewise, this one is sending -10 to this neighbor and -10 to this neighbor. Okay, so now what we have to do is add up the excitation and then subtract out the inhibition. So I'm not showing all of the other neighboring receptors. I've got a couple of arms coming out of nowhere because I just draw this to infinity. But this receptor is being struck by 100, getting -10 from this neighbor and -2 from this neighbor. It's a total of 88. And this one is 20 -10 -2, and that's 8, and there's some other inhibition for these others. So what I end up with is, well, a bunch of numbers down here. Nobody wants to look at numbers. Let me graph them instead. So what I'm graphing is distance along the x-axis, and then, well, neural activation along the y-axis. But that's not what I've labeled it. I've labeled it perception of lightness. If I get enough of these receptors together, more than just 4, maybe 400, I add up all of the activation and graph it. This is what the graph will look like. And it says, as I get closer to this sharp boundary, our perception of lightness increases. See how it goes from 80 to 88? And then it drops sharply from 88, boom, all the way down to 8, and then recovers back up to 16 again. Now remember what I said about the job of the visual system is, especially early on, detecting contrast. But the visual system wants to make sure it doesn't miss any subtle differences in contrast. So what it does by applying lateral inhibition, it exaggerates the luminance at the borders. It makes it bigger. It's kind of stretching it higher and then stretching it and pulling it down lower. So the difference from the peak to the trough is even greater. so that we are totally sure that there is a border there and we are not missing the border or the edge. Again, this is another important clue. Borders and edges are super important to the visual system. It's neat how illusions can kind of show us the workings of the visual system that otherwise we might not be able to explore and understand. Let's take a look at another illusion and see what it can show us. This one is very basic. It's not named after a person. It's just called simultaneous contrast. You might have seen this before. Again, it's about the simplest contrast lightness illusion that I can show you. The illusion is this. If you focus on the small gray squares in the middle here, they look like they're different. This one over here on the left looks a bit darker compared to this one over here that looks a little bit lighter. But let me take away everything else. Nope. Those gray squares are exactly the same shade of gray. But if I surround this one on the right by black, again, that kind of changes the lightness. And this kind of suggests to us that we don't see things the way they actually are, but perception is a bit more relative as opposed to absolute on a basic level. How can we explain what's going on here? Same idea, lateral inhibition. So this is a slightly different diagram. Each one of these funny cups you can think of as a photoreceptors, and we've got the stimulus kind of laid upon it. I can't draw all the lateral inhibitory connections. It would be just a hopeless mess. But we have to imagine that the photoreceptors under the gray square are getting inhibition from the other photoreceptors. Now the photoreceptors under the white part are getting highly activated, so they're sending a lot of inhibition to these poor photoreceptors under the gray part. These arrows are very wide, meaning there's a lot of inhibition, meaning the photoreceptors in the middle are firing at a very low level. Now the brain is going to interpret this as, oh, that's pretty dark there. Opposite is happening over here. So again, there are some photoreceptors under the gray area. There are photoreceptors that are, well, they're really not being hit by very much light at all. So these arrows are very skinny. They're sending a very small amount of inhibition, not a lot of inhibition affecting the photoreceptor in the middle. So it's going to be firing at a higher rate than its cousin over on the other side, which the brain interprets as, oh, there's more light on the right side than there is on the left side. So it looks like lateral inhibition is pretty powerful. It's accounted for 2 different lightness illusions so far. Let's keep going. Here's another illusion called the Hermann-Herring grid illusion. Some people call it the Hermann grid. Some people call it the Herring grid. I'm going to give credit to both of them. The thing with this is the illusion is something you're not looking at. If you look at the streets and the intersections, if you focus on an intersection, you can see that it's white and the streets look white. But off in your peripheral vision, at the other intersections, you'll see kind of grayish blobs. So if I look up here, yeah, way off in the periphery, there's some grayish blobs over here, but as soon as I look over here, it disappears. I can't see the grayish spots in my foveal vision, only in my peripheral vision. Well, let's see if we can use lateral inhibition to explain this. It's explained so many other things so far. So, in 1960, an explanation was proposed. It's all about lateral inhibition of center surround receptive fields. Now, in our periphery, we have larger receptive fields. In our foveal vision, in contrast, we have smaller receptive fields, which is partly what gives us our high resolution vision. So in this example, I am focusing on the upper left intersection here with my fovea with its teeny tiny center surround receptive fields. Over here in my periphery, I got big receptive fields. Now right here at an intersection, things line up to be perfectly kind of wrong. There's a lot of inhibition, but only a little bit of excitation. As a result, the brain interprets this as, oh, it's kind of dark here because of the inhibition. So the illusion arises because in our periphery, our center surround receptive fields are so big and they're hit by this problem. The tiny center-surround receptive fields on our fovea are picking up things accurately, and there's no problem for things that we are looking directly at. Okay, let's throw something else at this explanation and see if it sticks. What if we reverse the grid? What if it's white squares on a black background? Well, I don't know. Pick an intersection and look at it. Do you see some kind of light gray blobs at the intersections in your periphery? Yes, you do. How do we explain this? Easy. It's just the opposite kind of center-surround receptive field. It's an off-center, on-surround receptive field. It's beautiful. We can take what we know about the visual system and apply it to this, and it works. That's me dusting off my hands, because we are done here, right? Except for problems. Okay, here are the problems. We still get the phenomenon with grids of different sizes. Small grids, yep, you get the grayish blobs at the far intersections. With a large size grid, same thing. Now, the explanation that was proposed by Baumgartner in 1960 all depended on our center-surround receptive fields in the periphery being exactly the wrong size. Well, how can they be exactly the wrong size for both of these grids? That doesn't make sense. That explanation doesn't hold. Okay, that by itself is quite a problem. Here's another problem. Modifying the contours. Now, if you take a look at this figure, okay, clearly it's different from the one I've showed you so far, but if we think about it just a little bit more, there's a lot of similarity. There's like large, okay, black regions, and there are kind of white streets. Who designed these streets? And the streets do meet at a 90-degree angle. If you were to imagine the center-surround receptive fields here, they should still be producing the fuzzy blobs. But I don't know about you, but I'm looking at this and I don't see any fuzzy blobs at any of the intersections anywhere. Why should changing the contours a little bit totally erase those illusory blobs? I have an example for you, and this is linked on my website. This is Michael Bach's wonderful, wonderful gallery of illusions. And this one actually changes it from the completely linear version to the kind of twisted version. And what happens when it twists just a little bit, it's not even as twisted as the one I showed you, the blobs disappear. So if you look at it now, you'll see the blobs. And then as soon as it twists, boom, all those blobs are gone. What is going on? We can't rely on that explanation of center-surround receptive fields. There must be something else going on to account for this. It's a bit of a problem, but we're going to carry on anyway. Here is another lightness illusion called the Benary cross. And the illusion is that triangles A and B do not look like they're the same shade of gray. Now, if we're relying on lateral inhibition, the prediction is that both triangles should be the same shade of gray, because both of them are bounded on two sides by this kind of dark gray of the cross, and the hypotenuse is bounded by white. Same is true of B. The prediction is, due to lateral inhibition, both triangles should be the same shade of gray, but they seem different shades. We take away the cross and show you they are actually the same shade of gray. And again, putting it back, no, now they're different shades of gray. Lateral inhibition doesn't work. And this is a pretty simple illusion. It's not terribly elaborate or complex. Here's another one called White's illusion from 1979. We have these black horizontal bars and then the two rectangles, which I'll call A and B. Pretty clearly, A is a darker shade of gray than B. Let's look at the predictions made by lateral inhibition. It predicts that rectangle A should be getting very little lateral inhibition. So let's consider this bar. It's bounded by black on either side, so there shouldn't be a lot of lateral inhibition. This one should actually seem to be quite light, but actually it seems darker. And the same is true and opposite of B. This bar is bounded by white. It should be getting a lot of inhibition. It should be seeming very dark. But no, it's the opposite. It's lighter. Our experience is now the opposite of the prediction of lateral inhibition. It's completely wrong now. And I know you maybe don't trust me. Maybe I'm tricking you. So let me pull away the black bars, take them away. Yeah, I think it's pretty clear that all of these are exactly the same shade of gray. But I put it back, and now they're very different shades of gray. Looks like lateral inhibition isn't the entire story. Lateral inhibition is a form of bottom-up processing. It occurs at a very low level, according to the explanation. It occurs within the retina. But yet it can't explain these very simple, basic kinds of illusions. So how can we explain them? How about going to a higher level concept, a concept of belongingness? And this is the idea proposed by Gilchrist and colleagues. We will perceive any element relative to its surroundings, relative to the thing to which it seems to belong. It does seem to belong. So I won't show you these again. You can kind of flip back to them. If you look at the binary cross, triangle B, it seems to belong to the dark cross, so we see it as lighter in contrast to the dark cross. The same is true but opposite of triangle A. How about White's illusion? Again, rectangle B seems to belong to the black bars, so we see them as lighter in contrast to the black bars. Again, true but opposite for rectangle A, which seems to belong to the white part of the display, and it makes that seem darker in contrast. Okay, this is a kind of a satisfying explanation. It implies that there is some top-down, higher-order processing. It's not what's happening in the retina. Your retina doesn't know about belonging, what should belong to what. Rather, this is a much higher-order, top-down form of processing. I'll stop there.